A chemist investigated methods to improve the synthesis of sulfur trioxide from sulfur dioxide and oxygen. This is a combustion reaction, and the enthalpy here is negative because a combustion reaction is exothermic, and that means the enthalpy is negative. The chemist mixed together 1 mole of sulfur dioxide and 0.5 mole of oxygen with a catalyst at room temperature. Compressed the gas mixture to a volume of 250 centimeter cube, which is 250 centimeter cube, would then be converted to 250 over 1,000 decimeter cube, and that would be 0.25 decimeter cube. Allow the mixture to reach equilibrium at constant temperature without changing the total gas volume. At equilibrium, 85% of SO2 had been converted into SO3. Determine the concentration of SO2, O2, and SO3 present at equilibrium and calculate Kc for this reaction. At this point in time, it's better to write the equation again. 2 SO2 plus O2 2 SO3, and the stoichiometric mole ratio will be 1, will be 2 to 1 to 2. Just to remind you, this is 2, this is 1, and that's 2. If we simplify the stoichiometric mole, we simplify it. That means I divide everything by 2, I get 1, 0.5, 1. From the question, it did say 1 mole of SO2 and 0.5 mole of O2. So that happens to be the same here. So now what I can work out is the initial mole. In the beginning, we started off with SO2 and O2. So we have 1 mole of that and 0.5 mole and no mole of the product. At equilibrium, final mole, at equilibrium, we made 0.85 mole of, we made 85% of SO2 converted. So, which means that if 85% is converted, 85 divided by 100 is 0.85. What's left is 15%, which is 0.15 at the end in the final. And then if this is 1 to 0.2, that means this will be 7.5%, and that will be 0.075. We know to calculate the concentration, we need the volume. So the volume will be 0.25, 0.25, 0.25, 0.25. But because we're dividing mole over volume to get concentration, so the concentration will be, well, 0.15 divided by 0.25. So if I start the calculator, 0.15 divided by 0.25, and that gives 0.6. So concentration here is 0.6. Also, if I do 0.075 divided by 0.25, we get 0.3. And again 0.85 for that one divided by 0.25, we get 3.4. Now that we know the concentration, we need to write the Kc value. So the Kc value in this case would be Kc equals concentration of the product squared, because of the 2 here, divided by concentration of the reactant, that is squared as well, and concentration of O2, which is to power 1. And if we populate that with the concentrations, we're expecting to get 3.4 squared divided by 0.6 squared times 0.3. So if I punch that into the calculator using the fraction key, 3.4 squared, arrow key down, 0.6 squared times 0.3. Standard to decimal, Kc equals 107. The unit, the concentration squared, will cancel the concentration squared. And I'm left with 1 over concentration. So therefore, the unit will be per mole decimeter cube. Now, question 2, part 2. Explain what would happen to the pressure as the system was allowed to reach equilibrium. As the system is reaching equilibrium, there will be less of the reactant because they've gone to form product, which means the pressure will start to decrease because there are more reactant than the product. This is 2 plus 1 as 3. So if you look at the number of moles of the reactant, altogether add up to 3, and the product is 2. If you're converting 3 particles to 2, the pressure will go down. So we can then say that pressure will decrease because you're going from 3 to 2, and fewer molecules formed. Part 3. The value of Kc for equilibrium. For this equilibrium decreases with increasing temperature. Predict the sign of the enthalpy change for the forward reaction. States the effect of the equilibrium yield of SO3 of increasing the temperature at constant pressure. As you can see, the reaction is combustion, which means it's exothermic. All combustions are exothermic, which is negative. What that meant is it required less heat So if it's negative, it means it doesn't need too much heat. If you increase the heat, the product will go back to the reactant. If you decrease the heat, the reactant will go to the product. So increasing the temperature will make reaction go back to the reactant. So we can say delta H is negative because it is exothermic, because a combustion reaction. Increasing the temperature will cause reaction to go back to reactant. So therefore SO3 will decrease. Right. So if you increase the temperature, the yield of SO2 will decrease. Because this is negative, it means it doesn't want higher heat, it wants low heat. And if you increase the heat, the reaction will go backwards. If you decrease the heat, the reaction will go forward. Part 4. It says here, the chemist repeats the experiment at the same temperature with 1 mole of SO2 and an excess of O2. The gas mixture was still compressed to a volume of 250 centimeter cube. State and explain in terms of Kc how the equilibrium yield of SO3 will be different from the yield in the first experiment. So with the experiment, Kc only change with temperature, not with pressure and concentration. So we know that Kc will be the same because only temperature will affect Kc, not concentration or pressure. So, but at the same time, if we increase the value of O2, what that meant is more O2 will collide with SO2 to then form SO3. So the concentration of the yield of SO3 will increase. So SO3 will increase as O2 increases, while Kc remain the same. So we're saying that the Kc will be the same because only temperature will affect Kc, not concentration or pressure. SO3 will increase as O2 increases, because if you increase O2, then there are more O2 to collide with SO2, hence to make SO3. So therefore, SO3 will increase. And as you can see here, you're increasing SO3 and you're also increasing O2, which means Kc itself will still remain constant because SO3 is in the numerator, O2 is in the denominator. And therefore, as SO3 increases, when O2 increases, and while Kc remain the same.